Do you want to share?
Mhm.
Because you're gonna have to do the Tinkercad stuff anyway.
Yeah. All right, so today's pretty simple agenda. We're gonna go through the CODR presentation that you guys put together, and then we're gonna move into our next unit after Python, which is learning some basic CAD. So let's start with some CODR stuff then. Payload 1, you want to go first?
Okay, I suppose I'll share. Okay, so we're payload 1. Next slide. So we have our mission statement, our success criteria, our timeline, expected results, and brief design overview. Next slide. So our basic mission statement is this experiment is going to measure radiation and heat to find out what altitudes will cook certain foods without a dangerous amount of radiation. The reason for this experiment is because we are hungry and want to measure radiation in the atmosphere and represent it in a fun way. We will also learn about the types of radiation and how they vary at different levels in the atmosphere, also space cooking. Next slide. So the minimum success criteria is we want our radiation sensor data to be retrieved successfully. So we want at least a bit of data so we can see how the radiation levels vary in the atmosphere. And we also want to be able to find and retrieve our CanSat. The comprehensive success criteria is getting and understanding pretty much all the data, the food in our CanSat surviving, getting pictures, and it stays operational, so it doesn't like fall apart as it comes back down. So our approximate time, so we want to load the food 15 minutes before because we don't want any other variables to like affect the food because we want to see if it's still safe to eat and like how much the radiation affects it. 10 minutes before, we're power on all our systems. Temperature control is pretty important for us because if we want to cook the food, we don't want unknown variables affecting what we're trying to measure. And if we have enough time, we want to try to be able to transmit data to a ground station. But if we don't have enough time to be able to do that successfully, we can just retrieve the data when it comes back down. We launch it, and with 80 minutes after launch, the balloon will burst and it'll start coming back down. The parachute will deploy 2 minutes later and it'll land 180 minutes after we launched it. Next slide. So what we want to happen is we want to measure the radiation in the upper atmosphere, which we want to measure several types of radiation. We want data on what foods you can cook in space. And some people did an experiment and they showed that marshmallow, we were thinking of doing a s'more to test, and marshmallows evidently get denser as they go up into space. So we're expecting that to happen. Next slide. So we didn't draw a design overview, but we definitely need temperature control so we don't have unknown variables in our experiment. We definitely need radiation sensors because that's what we're measuring, that's what our experiment is about. And we'll need food in our CanSat to see if it'll be cooked and how much radiation it'll absorb. We don't know what food we're going to use yet. We're kind of leaning towards a s'more, but we don't know yet.
All right. That's all. Good job. Any questions from anybody about that? I guess I have a quick question. So on the, where is it, on here, you said that it's going to be continuing data collection starting at T plus 80. Is that something that's just going to be happening once the balloon bursts, or is that going to happen throughout the entire flight?
Well, we want to have the data just transmitting throughout the whole thing, but if we don't have enough time to be able to program and like do that successfully, we can collect the data when it lands back down. We want to be able to continuously transmit data all throughout the whole flight, but we don't know if we're going to be able to do that yet.
Okay. Yeah, any other questions? No? All right, well, good job, Payload 1. Next, anybody from this group want to present?
Sure. We have or Payload 3. Me, well, Casey, Andy, Dylan, and I. Next slide. Our overview is we first have a mission statement, then objectives, then concept of operations, then expected results. So mission statement is we are testing better hooks as well as how the sensors react at a high altitude, specifically radiation sensors, and using silicon cells if possible. This will allow us to know more clearly what will happen on the CubeSat. We'll be using a nanosat to achieve this. Our objectives are to see how a low cost CubeSat parts will react in a high atmosphere. Have a pre-test to learn about how things might need to work when we are in space. Learn how to better work as a team and what our strengths and weaknesses might be, and learn and grow together. Our success criteria is we will know if our mission has succeeded, if we are legally and successfully able to collect, receive, and understand data taken from the nanosat and the high altitude balloon. Then our concept of operations, how I expect it to go, is first, of course, we'll launch the nanosat and the high altitude balloon. Then we will record that data. After some time, the balloon should fall, and so at that point, all we need to do is find the balloon, and yeah. We expect that the high altitude balloon will launch into air properly, produce helpful and important data for scientists and students, transfer data from a remote location not requiring physical access, land successfully, and learn more about radiation sensors and silicon panels to better prepare for a perovskite study on the Big Red Sat. Then the nanosat overview is it has radiation sensors in it, silicon panels if possible, and for the high altitude balloon it will have better hooks, so hopefully they don't break. And then Dylan, before he left, had a video I wanted to show.
Two puppies. Okay. Any questions for this group?
I have a quick question. If you go back a few slides, you said legally like retrieve stuff. What does that mean exactly?
Not have it go into a place where you can't get it, I guess.
Okay. All right, that makes sense. All right, thank you. I just wasn't sure what you meant by that.
I had a question. If you can go back to the objectives slide, please. So on here, it doesn't really mention anything about silicon cells, but I know that that's something that you mentioned earlier, Robert, and that has like kind of been thrown around. Do you have any more information on that? Is that just like, hey, this would be neat if we can add this on if we have time, or kind of what's the vibe, I guess?
It's more of it would be nice if we could add this on if there's still time.
For sure.
Mhm.
Any other questions for this team? All right, well, good job, Payload Pi. Next up, oh goodness, is Payload 2. Anybody from Payload 2 want to present?
I can do it.
Cool.
The thing with our payload is we kind of had lots of ideas we didn't really know what to do with, so we kind of factored 3 designs into one. And we kind of want feedback if that's feasible or like possible with the weight and money we have.
Okay.
Okay, so our first one would be payload silver, which would be testing how bioluminescence of a fungus is affected by radiation. And what would be cool if we got some photos of that. That's kind of optional. Payload shadow is like, it's kind of reused of like the old payload idea for the CubeSat. It's like test if fungi can absorb radiation. And then payload tails is to just gather knowledge. Like we'd make our own homemade perovskite cells, and like we would gather knowledge that'd be useful on the CubeSat. Oh, next slide. Okay. And we want to do this in the environment the high altitude balloon provides for us to test the effects of radiation on mushrooms' bioluminescence along with their ability to block radiation. Our minimum success criteria would be just gathering the data we get, and our maximum one would be getting like all the data and maybe get some pictures and have everything work well. This is just the concept of operation. "10 minutes before launch, we would load up the mushrooms. In 5 minutes, we'd turn on all the electronics and start a data collection. Then it would launch, and then the balloon would take its path and it would land, and we would collect all our data and equipment. Our expected results for payload silver is that the mushrooms will increase their glow intensity due to the radiation. For payload shadow, it will be that the mycelium lowers the levels of radiation. And for payload tails, we just know that it's going to gain power, and we're going to see how that works and gain the experience on building those. For payload silver, we'd place photoresistors on an area outside where the glow mushroom is concealed, and we would use that to measure it during the flight. For payload shadow, the fungi will be placed around a radiation sensor, and it'll measure, it'll place around, and it'll the radiation sensor inside will measure that. We also have one outside the mushrooms to like see what it'd be like without their presence. And for payload tails, we'll have the solar cells mounted kind of outside the blind box.
Oops. Sorry, I went too far there.
And this is like a diagram of what it would look like. As you can see, we have the mushrooms inside the radiation sensor, around the radiation sensor. We have a photoresistor looking at the bioluminescence ones, and the perovskites mounted outside the box.
Okay, awesome. First of all, does anybody have any questions for Payload 2? I guess one question that I would have is, do you have leads on acquiring either type of the mushroom yet?
For the bioluminescence one, we aren't completely sure which one we're going to use, but we have some ideas. For the mycelium, we found like a kit that would allow us to like access it really easily.
Okay.
For the bioluminescent one, can you hear me?
Yeah.
Yeah, we, MJ and I were able to find a mushroom that we could use. So it's going to be foxfire or Pinellus stypticus, whatever it's called. So, and it seems to be reasonably priced. So there's that.
Okay.
We were able to find sources for everything, both of the mushrooms and the perovskites. The only question is like shipping. The 2 mushrooms would probably come from Etsy, which can be a little bit of a gamble as to like when the shop sends things. But I sent them a
Yeah.
message and they said that they are usually pretty on it. I don't know what that means, but
Okay.
If you aren't able to do all 3 payloads, do you have a preference for which ones you want to focus on?
We haven't really discussed that yet, but
Yeah, that's fair. Just, yeah. Okay.
So how big do you think each payload would be?
the perovskite one would be more on the outside, and the other 2 would be split on the inside.
So like if we have like the inside of those coolers is like maybe, 5 inches across by, I mean, the height's adjustable, but let's say like 6 inches tall. Is that enough space for you to fit both mushroom payloads in there?
Yeah, I think when I looked, most of the mushrooms, well, at least the 2 mushrooms that we're going to be using, I don't think they went past a couple centimeters in
Okay.
size. So I guess it just depends on how we pack it.
Okay. And then are you going to have any sort of temperature control that you need? That you know that that's not a variable as well?
We were looking into that, but we hadn't fully like decided yet.
that was where the biggest weight problem was going to be. Everything else is relatively light, and the temperature control is going to be the biggest factor in weight because we don't want the mushrooms to freeze.
Yeah. Yeah, I think that's a special systems thing for all of the payloads, really. Okay. So in terms of, like you said, you wanted feedback on feasibility of all of these. The perovskites might be more difficult to get because we're working on that right now with John McClure, but we don't have, as of right now, a company like finalized for getting those from.
Well, these would
Go ahead, MJ.
like the ones that we were going to use here, they would be like we'd buy a kit that we could just make. So it would just be like we're just buying one. So it
Oh,
just
okay.
would be the longest factor of how it would get to us.
Cool. With no other questions, yeah, good job, Payload 2. All right, Payload 4. Anybody want to talk about this?
I can. I don't think Alyssa can right now. So this is for the special systems sub-team. And so what we're going to be doing is the main center point is testing the field strength of the Earth's magnetic field with the varying altitudes. But we found some scientific paper that suggested that living cells absorb more radiation at different magnetic field strengths. And so we want to attempt to test that. Going on the next slide. So using the environment that's provided by the high altitude balloon, we want to test, because we have a pretty varying range of altitudes. We want to see how, with the changing magnetic field, if a collection of living cells will absorb or reflect more radiation, or reflect less, absorb more radiation at very high altitudes with a dramatic change in Earth's magnetic field. And as well as observing that change, we also want to just make a graph of the magnetic field strength versus the altitude. So for our minimum success criteria, we want to retrieve the payload and collect some data regarding this field strength, and we want the living cells to survive the trip. For comprehensive success criteria, we want to build actual graph models for the altitude versus magnetic field strength, as well as have some sort of graph or model of how much radiation is absorbed by living cells with respect to the change in the magnetic field strength of their environment. So the concept of operations is kind of the same as what we've seen so far. We're going to launch from UNO, or the SAC Museum, ascend at a set rate based on our balloon. Apogee will be about 110 to 100,000 feet in about 80 minutes, and then we'll descend with the first free falling, then with the parachute at 20 feet a second descent rate, and we'll land in about 180 minutes. That's kind of already been said. And this is the same stuff, but in table form, and also showing what we're going to be doing. So we'll load the living material around 10 minutes before launch, just to ensure that nothing can really affect it. Start data collection, turn everything on. A few minutes after that, we launch. We will be, I didn't write it down, but we will be collecting data continuously throughout the mission. We'll hit apogee around 80 minutes, parachute deploys, assuming everything works, about 2 minutes later after free fall, and then we will land and retrieve it, in which case we'll retrieve the recorded data in the payload. So we're expecting to see at a higher field strength, so at high altitude, we'll see that the living cells will reflect less, or rather absorb more radiation or light. And additionally, we expect that the field strength won't increase linearly because we're not going straight up, but it will increase with altitude. And then for the design overview, the living cells would likely be something we can easily get. So like potato cells is something that I believe Alyssa found that are really good at reflecting radiation. Or chicken embryonic cells, in other words, egg yolk, because you go to the store and buy them. Or a mammalian culture that we haven't yet decided on, because you can just buy those online. Those would be closest to human cells, obviously. They'll have to be kept in some sort of incubating container, that is just to be heated and not have massive pressure changes imposed on it. So something that's probably airtight. The magnetic field strength will be measured using a magnetometer Arduino component, because they're pretty easy to get, and there's a wide array of them. So we don't know which one yet, but those components exist. And then the data collection will likely be ran using a Teensy or Arduino microcontroller. Raspberry Pi options also exist, but they're just a bit more expensive than the Teensies. That's it.
Okay. Sweet. Any questions for anyone about the special systems payload? I guess I had one kind of, the field strength will increase with altitude. Why? I thought it was like the closer you were to the center, it was stronger.
It's a dipole, or Earth's magnetic field is as a dipole. And so as you're closer to the surface, do you know, I guess I should have put a picture in there. The dipole kind of looks like this. And the surface of the Earth, at least unless you're at the North and South poles, is kind of, maybe I'm wrong, it might be the other way around. I guess we didn't really look into that too long. But because of the dipole shape, we're expecting to see it gets a little bit stronger with altitude, and we won't be so far out into space where you start seeing dramatic effects. So it should get a little bit stronger because of the dipole shape of the field.
Okay. Okay. Any other questions for payload 4? All right, well, sounds good. And the other two payloads are testing, correct me if I'm wrong on this, it's like some of our global star or satellite communication systems, and also I think a camera module, one of them.
I believe we're also testing the XB again to see if we can get that working on the other one.
Okay,
So radio communications as well.
cool. Are we gonna have a ground station for that?
Possibly, if we can get it working.
Okay. Joel, do you have any comments, just kind of overall CODR comments for everyone? I know you were kind of the expert on this. Or Karen, do you have any feedback on how this looks as CODRs?
No, not right now.
Okay. Okay, so I think we're going to move on then from those CODRs. And the next thing that we're going to talk about is CAD. So we already talked about some Python stuff with Joel, but now we're going to move into our next unit, which is learning about CAD. So CAD stands for computer aided design, and it's what we normally use SolidWorks. However, SolidWorks is kind of difficult to use if you're just getting into CAD, and it's also hard to get licenses, because if you don't have a license through university, it's like $2,000 or something. So there's this new site called Tinkercad. So if you go to tinkercad.com, it's free, and you just need to sign in with your Google account. So I'm going to post more about this probably later, like post the challenges and stuff. But when you go into Tinkercad initially, there is a short tutorial that I'd recommend watching. But here's just kind of an overview. So if you create a design, it calls it weird names. It has very creative naming conventions. But you go in, this is your work plane. In the top left here, you can adjust the view that you want. Then over here, you have all of these basic shapes that you can use. So you have basically solid shapes, and then you have hole shapes. So the hole shapes are like negative space. So if you put a hole shape, it's like having a giant hole there, the shape of this box. So then once you have a shape, you can adjust it in all 3 dimensions. You can move it, and you can rotate it. So there's the box, there's the cylinder, which is much the same thing. You can actually click on this drop-down menu if you want more precise control. There's spheres. There's different like triangle shapes. There's also this cool scribble thing, which you put in. Yeah, and like you can make different shapes. And then it comes out as like a full shape. So you guys can kind of explore these on your own, but there's also other options like text. And there's quite a few pre-made shapes that it goes through. But once you have the basic shapes in there, you can also do a lot with combining them. It's like, say, let's start with this box right here. So say you want to make another box cutout in the middle of this. So you have this little negative space box. And when you can select the two components just by clicking on one and clicking the other. Come on. And then this button right here is the group button. So if you group them, then it just combines them into one shape. See, now you have a box with a hole on it. You can also combine shapes that are solid. So we have this cylinder. So you want to move it up and combine it, or move it to the side and combine it with this box. Again, if you click like that, you can group them. And now it's all one shape that you can manipulate. Then, of course, if you want to ungroup everything, there's an ungroup button. So now you have, it just does like one at a time. So now you have a bunch of individual shapes that you can manipulate again. So Tinkercad is advanced enough that you can make some cool designs with it without being overly confusing. Here's one that I made. It's a Lego brick. So this is going to be your first challenge after today. It's tilted. You can change the tilt on it, but I just wanted to be able to see the underside as well. But yeah, and then the nice part about Tinkercad is once you have these shapes, you can change the size of them, and you can actually export them as an STL file so that they can be 3D printed. So hopefully once we have our Hab build days, maybe you all can come with some CAD designs and we can print them out so you have actual like CAD mementos. But there's also, let's see, where is it? That's one of them. I also made, oh yeah, so these are all public. I'll put the links in later. So that Lego brick is one challenge. And then the CubeSat, this is, once you get through the first challenge, your second challenge is a CubeSat like this, which probably looks really complicated, but it's actually just a bunch of sides combined together. Oh, I didn't, okay, yeah, sorry, there's one more thing you can do. It's called aligning things. So if you have these two shapes, if you click this button called align, then it gives you all these different options. And you can align them, like if you want to align them center like that, if you click like that, it'll combine them into that box. it's a little bit hard to explain while it's on my screen, but if you have this align button, it'll allow you to position shapes exactly where you want them, so you can merge them into something that makes sense. I know I kind of covered a lot, and there's a tutorial, like I said, when you start Tinkercad that will probably be helpful as well. But are there any questions at this point?
When you're making stuff, do you feed it like units, like inches and centimeters and stuff like that, or how is it determined that?
Yeah, you can. So there's the ruler. I think, okay, so you can set the ruler here, and that just kind of changes the units that you're working in. But then when you have each one of these shapes, you can change the dimensions there as well.
Oh, and right now it's in units of millimeters.
Yeah,
Okay.
the snap grid too. Yeah. I think it's always in millimeters. I haven't found an option yet to change it to inches, but since millimeters are the superior unit of measurement.
That's fair. Okay, thank you.
Yeah.
What's the edit grid? At the
Edit grid.
bottom. Yep.
Oh, there we go. Okay, yeah. Yeah, I guess you can change it to the
The
inches.
bricks.
I don't know what the bricks is.
Just some weird like imperial unit that.
Yeah, I guess.
Wait, look at your block. It has like 2 layers now. With Lego
Yeah.
brick?
What? No, that was there before.
Oh, okay, okay.
Evan said that brick makes actual Legos.
Oh, really? Okay, that's cool.
Interesting.
So is it like one stud then is a brick, or is it?
He says at the top is a Lego brick that makes Legos.
Top right corner, John. Right there.
Oh,
Oh my god, that's sick.
that's amazing. Yeah,
That's dope. Okay, I'm sorry. That's awesome.
that's
You should-
really cool.
Class.
What do you say?
I said Evan should be teaching this class. You're gonna get replaced.
Absolutely, yeah. Okay. Well, that's a good way to make Legos then. But going back to the Lego brick, that's the first challenge. This is going to be a little bit bigger than just one Lego brick. So I'm going to link this in the Slack. And I think you should be able to maybe edit it that way. Can someone confirm, or does it have to be from a yeah. Turn the Lego into Lego? Oh, because it's tilted. Yeah, that's okay.
At
Didn't
the top left corner, change the
Yeah.
Ooh. I like it. See,
That's
if you're
cool.
3D printing with Legos, that's what it would look like.
Yeah, I'm curious to see how that actually 3D prints. Oh, you can change the layers as well on this part. Yeah, that's neat. We should make Mikey said you should make a 3D printing machine out of Legos.
So guys, so with this tool, is there what kind of stuff would you guys like to make with this? Not necessarily just the Lego one, but just in general. Like you have this program at your fingertips now. What kind of stuff do you want to make with it? Andrew says a 3D printed pneumatic engine. That'd be pretty sick. That'd be pretty sick.
It'd be impressive if you could make that.
Pneumatic is where they use like the air through tubes to make stuff work, right?
Yeah.
Don Helzer, you're an engineer.
Yeah, it is.
Okay, thank you.
That'd be crazy though.
What else do you guys want to make with this sort of program? I feel like pirating Lego sets might be a common one among people with this one. It seems like. Andrew, other Andrew, yeah, it is. So this is going to serve as a basic intro into the world of CAD. So it's going to kind of get some of the core concepts down of how to make 3D models with this type of software, and possibly in the future we can upgrade to something more like more widely used like SolidWorks or something like that.
Mm-hmm.
So this is just kind of serving as an intro to that sort of realm.
Yep.
Do any of you have classes at your schools where you're like engineering type classes where they have software you can use? So what software does your school maybe have available to you? You have like Project Lead the Way courses? Okay, Tinkercad.
What's Homestyler? Gotcha. Is that just something that's used for kind of architectural projects, or is it for all kinds of CAD models?
So like rooms and whatnot, right? Cool.
Okay, cool. Has anybody ever used Autodesk Inventor? Yeah, listen, you have. Is that? I think I looked into that at one point, but is that free licenses or is that cost money?
I'm wondering if some of the schools have, just like we have SolidWorks at the university, if some of the schools have Autodesk Inventor available at no charge to the students.
Oh, there's a student thing. So, yeah. Karen, do you know if it'd be possible to see if UNL has any licenses for Autodesk Inventor?
Yeah, I think we can check on that. And then the other thing we can also do, if we don't have it, is see if they would be willing to license it to our team.
Okay.
Also, with Tinkercad, I didn't notice this till just now because I'm using it in my computer right now. There's a circuits option where you can design like Arduino circuits
I did
on
not
the
see
left
that.
side of the screen. Do you see it under 3D designs?
Oh yeah.
That's dope. I haven't used that yet personally, but this seems like something that if you guys want to play with, I would highly encourage it because this will not be the end of your using Arduino.
Yeah. Okay.
That is very, very cool.
That's
But yeah, I
awesome.
just wanted to kind of bring attention to that.
Huh. Yeah, I'd never heard of Tinkercad for anything else, but it looks like it has code blocks too. So you can code. If you want to go back and see any of the other lessons too from the tutorial, here's if you go to the lessons tab, so you can go back and rewatch things if you have questions about anything. But yeah, so at some point we might move into Autodesk Inventor or some other kind of product. But for now, just to kind of get the basics down because it's free, so you guys can kind of start 3D printing some stuff on your own. Tinkercad is what we'll work with. So can anyone confirm that the link I sent in Slack works and it doesn't just, it's not just like a link that only I could access because it was my account?
So it is a link that just takes you to like a general page. Like, so if you don't have an account, you have to make your own.
Okay.
Did you make like a classroom for this? So you can just send people like the class code, or
I haven't looked into making classes yet because I thought you could just export it, but actually, okay, if I sign out, maybe I can search for it because I know it's on public. It's a public. Interesting. Yeah, I'm gonna have to find a way to share that because I thought that worked better. It did. Oh, the Inventor for Students is free. How advanced are those designs that you can do? Like, does it have just a free trial or is it free forever?
Okay. Alyssa said it looks like, yeah, inventors for Easter students, and then for SolidWorks, it's like SolidWorks in terms of advanced, and there's a trial if the student one doesn't work out. So like students get a free account, and then if that doesn't work, there's a temporary trial.
Okay. How long is the trial?
Are you?
Here's your- What?
I was gonna say, are you done like kind of giving a tutorial? Like,
Yeah, and I put the link in the general, so that link should actually take you to the Lego brick if you have questions on how to make it.
so I think for the rest of the meeting, we're gonna have work time, just kind of in CAD. Does anybody have any questions before we move to kind of going in breakout rooms and the usual stuff? No. Sounds good.
Just in terms of timeline on the CAD projects, I was thinking a week for the first one. That should be long enough to, especially with the work time we have here at the meeting, to make the Lego brick. And then if you get done with that one, here's a link for the second one, which is a CubeSat model. Ignore the little thing there. I'll take that out. Yeah, we're done. CAD for now.
Okay. Do you want to split people up into breakout rooms and then get started on work time?
Yep.
Nice.
Are you thinking breakout rooms according to payload?
No, just kind of random.
Okay. So we have.
Or well, I guess before we do that, we should probably take a break. We've been here for an hour, halfway done. Everybody
Okay.
can stand up, go to the bathroom, do 1.5 jumping jacks, sit back down. Fun activities. Okay. Give me 1 second.
Today was our first major test flight, which is usually just does the plane fly.
All right, hold it back.
So would you say that, today's test flight was a success?
I would say it's for the most part a success. Even though we didn't get off the ground, we definitely did get information and feedback, which is what the people we meet with today, they're old. They know, they got them old knowledge, So they've flown before, they know what problems can exist and they know what to look out for. And I mean, even though our tail broke off, I mean, they told us what we can do to stabilize it. So it's not going to be hard to fix it, and we can definitely do that.
Oh, holy shit. They just got plenty of power. Way out of trim. It's all over the place.
Can you talk a little bit about what happened today compared to last time?
We actually got off the ground, and we got off the ground twice and got back on the ground twice without any major damage. So theoretically, we could grab that plane and fly again.
What do you think the major difference was between this flight and the last one?
That tail, we beefed that thing up. I like how it looks though. It looks pretty nice and looks strong compared to last design, but that tail was definitely what put us in the air this time.
What are next steps?
We first got to look at payload design and sensor design, and then some deployment and retrieval mechanisms, and then probably prototype number 2. Redesign some of the things there and fix a lot of the issues and improve on accessibility in certain areas.
So for each of the prototypes, do you completely rebuild the plane?
Yes. The only things, I mean, we may or may not use the same engines. I think we usually change out, or at least change out the propellers. But we do a complete overhaul. We might take some things from the last plane, but usually we do a new wing, do a new fuselage, do a new, just overlook the entire thing and kind of build on top of the mistakes of the last plane. If you want to watch things fly, come. If you want to watch things crash, still come. We might have a crash every once in a while. If you want to see things getting off the ground, I mean, we got off the ground this time.
Technically, you got off the ground last time.
Let's go.
All right, I'm going to see if this thing will land.
Irrespective.
We
of
still
the
haven't
actual
done a
design.
single thing to actually accomplish the task at hand.
Well, we designed an aircraft.
It does go in the air. That is,
Yeah.
we can call it an aircraft now.
Ooh.
Woo! Wow, that's impressive.
So we talked about this a little bit last week, just how, like, you know, failure is a part of any design process. And I know that, like, at least when I was in school, failure was like the worst possible thing. Like, if you didn't get right on the first try, you know, it was over. Like, you didn't really have a chance to do it again. And I think that it's really important to know that, especially in engineering, that the quite opposite is true. If you got it right on the first try, you probably did something wrong, or you probably, you know, could have been more innovative, could have, like, added some extra steps, could have made it harder for yourself. And so, like, you know, just in a week, you know, you saw the evolution of this plane. It went from, you know, the propeller flying off and the tail snapping off and all that kind of stuff. And then a week later, you know, they got advice from some of the people who were there from the Lincoln Sky Knights, and they fixed it up, and they flew it twice. They flew once and then it landed, and then they were able to fly it again, and it landed, and honestly, it probably could fly again if it needed to. Nothing was broken, and it was really cool to see. So I hope that, you know, if at any point in this process, if we run into some troubles with our designs or anything like that, I hope y'all don't get discouraged, and just know that, Mikey, you're gonna hate this, but it is what it is. And yeah, it'll be cool.
It is what it is. What is that from, actually?
from TikTok.
Yeah, I'm opening the breakout rooms. Well, people are already in, so I'm just going to broadcast a message and also say it here.